Alright, this is part one of our videos on experiments. This is kind of a lengthy topic, so we're going to take it in parts here. Um, the first thing I want to do is talk a little bit about what exactly an experiment is. So sometimes the questions we are trying to answer deal with the effect of certain explanatory variables on some response. Such questions are often of the form, what happens when, or what is the effect of. For example, an educator may wonder what happens to test scores if an activity-based method of instruction is used rather than a traditional lecture method. An industrial engineer may be considering two different workstation designs and might want to know whether the choice of design affects work performance. A medical researcher may want to determine how a proposed treatment for a disease compares to a standard treatment. A nutritionist working for a commercial bakery may want to determine the effect of baking time and baking temperature on the nutritional content of bread. To address these types of questions, the researcher conducts an experiment to collect the relevant information. The value of some response variable, like maybe a test score or an assembling time or the bread density, is determined under different experimental conditions. Experiments must be carefully planned to obtain information that will give unambiguous answers to questions of interest. So an experiment is a planned intervention undertaken to observe the effects of one or more explanatory variables, often called factors, on a response variable. So we want to determine, can X affect Y? And more importantly, if the experiment is done correctly, we can actually determine, will X cause Y. So X is the explanatory variable, Y is the response variable. And we sometimes call the explanatory variable factors. The fundamental purpose of the intervention is to increase the understanding of the nature of the relationship between the explanatory and response variables. Any particular combination of values for the explanatory variable is called a treatment, and we'll talk more about that later. Now, the design of an experiment is the overall plan for conducting an experiment. A good design minimizes ambiguity in the interpretation of the results. So we really want to have a very good design, and a good design will make sure that your results are very clear. They will make sure that your results say that X causes Y, nothing else. So we want to make sure that a good design gets rid of any kind of iffy ambiguity into the problem. Sorry. There are three different types of designs that we will discuss. We'll talk about two of them in this video, and we'll talk about the other one a little bit later. So let's start with a simple example, okay? Let's say that I, as a teacher, want to determine if the room temperature has any impact on student scores. So if I simply say, okay, well, I teach algebra, right? So I'm going to have my block 1 class take the tests in 65-degree room temperature, and I'll have my block 2 class take the tests in a 75-degree room temperature. And what I want to figure out is, does the room temperature cause higher test scores potentially? So maybe I find out at the end of this simple study, I find out that the students in block 2 had higher test scores. So does that mean that a higher temperature in the room will cause higher test scores? Well, the answer to that hopefully should be absolutely not. Now, the reason for that is there's many other factors that could potentially determine a student's test score besides just the temperature. So let's kind of list a few. So I want you to kind of think some, and hopefully, obviously you can't tell me right now while you're watching the video, but hopefully I bring apart some things that you're coming up with. So one thing that can determine how a kid does on, say, an algebra test. So let's say the response variable is their score on an algebra test. So what kind of things can determine the score on an algebra test? Well, how much time a kid studies, right? Who their teacher is. Maybe if Johnny has a different teacher than Sally, Johnny does better or Johnny does worse. What time of day they take the test. Some people have said that taking math tests in the morning is better than taking math tests in the afternoon. What else here? What textbook they used? Maybe Johnny used a different textbook than Sally, and potentially that textbook is a better textbook, and that's why Johnny did better. Maybe it was the instruction strategy. Maybe one student's teacher used a better instruction strategy, like maybe it's the flipping the classroom, or maybe it was more activity based, where they did a lot of activities, or maybe it was just pure lecturing. Um, what was the level of the students? Maybe the one class did better simply because it was more honor students in that class, and the other class did worse because there were more lower level students in that class. So as we can see, there are many other variables that could potentially cause a higher or lower test score besides just temperature. Now, our study is interested in temperature. That's what our study was interested in. So any other variable that could cause my response to change is what we call an extraneous variable. So once again, my study is focusing on, can the room temperature actually affect how a student does on an algebra test? So anything else that could potentially change that response is known as an extraneous variable. So a good experiment cannot possibly show cause and effect unless a lot of these other variables are controlled for. Okay, so one thing we can do to make this example better is we can try to control some of these extraneous variables. So one thing we can do, real simple, is we could take care of the textbook real simple. We can make sure every student uses the same textbook. Pretty simple. Another thing we can take care of is instructional strategy. We can make sure that every single kid has the exact same instructional strategy. Maybe it's all lecture, maybe it's all activity based, but we want everybody to be the same. So what we're trying to do here is we're trying to establish direct control. And direct control is a very important part of any experiment. And what direct control is implying is that you want to control every single thing in that study except for the room temperature, right? Because the room temperature is what you're going to actually change. You're going to make one room 65, one room 75. What are some things we can't change? Well, maybe we can't change who their teacher is. So one teacher has Mr. Lipinski, one teacher has Mr. McNair. We can't change that. Something else we can't control. We can't control how long a kid studies for. We can't control if one kid is an honors student and another kid is not. What time of day they take the test. We can't necessarily control for that. So one step to establishing a good experiment is controlling what you can. So something as simple as making sure everybody uses the same textbook, everybody uses the same instructional strategy is a way to establish direct control. So that can get rid of some of those extraneous variables. Now another strategy we can use here is called blocking. Okay. Now blocking, you can only block on one variable at a time. So I'm going to write that down. One variable at a time. So we have to choose what is one variable that is extremely extraneous, right? What is one thing that can definitely have a major impact on their algebra test score? Well, maybe that's the teacher. Right? We definitely know that the teacher has a big impact on it. So rather than having, all of these block 1 kids all have Mr. McNair and all of these block 2 kids all have Mr. Lipinski, where all of a sudden, is it Mr. Lipinski that made them have a better test score, or was it the temperature? So what we want to do is we want to block, and here's what we do for blocking. Let's say that we have 50 kids, right? 25 of them have Mr. McNair, and 25 of them have Mr. Lipinski. So what we do is we block on the teacher. So we purposely, not randomly, we purposely put them into 25 Mr. McNair, 25 Mr. Lipinski. Then of Mr. McNair students, we put half of them, so maybe that's 12, into the 65-degree room temperature. So that's one treatment. And we put the other 13 into 75-degree temperature. And for Mr. Lipinski, same thing. We put 12 of them into 65 degrees, and we put 13 of them into the 75-degree room. This way, we have students in Mr. McNair taking both tests, taking both temperatures, and we have students from Mr. Lipinski's class in both temperature settings. That way, we are blocking on teacher. That way, somebody can't come back and say, oh, those kids did well just because they had Mr. Lipinski. No, 75 degrees students, some of those students came from Mr. McNair as well, and they did good too. So maybe it really shows that the 75-degree room temperature really did have a better test score. Okay, so blocking is one way that we can control for one extraneous variable at a time. You can't, unfortunately, you cannot block for more than one. So that's one way we can take care of it. Okay, so now we could take care of the teacher. Now, what about these other variables we talked about, like studying or what time of day or level of students? Now, how we could take care of that is by simply using randomization. Okay, so these are three of four main ideas. We'll label them as 1, 2, and 3, and we'll talk about the other one here shortly. And basically, randomization will say, okay, you know what? Well, as long as we choose which 12 go into the 65 and which 13 go into the 75, as long as we choose that, and I'm going to use a different color here so it stands out, as long as we choose who gets what randomly, I'll put an R there for randomly, what that tells us is that through randomization, it would be very likely that some smart kids get put into the 65-degree temperature room and some smart kids get put into the 75-degree temperature room. Some lower level kids get put into the 65 and some lower level kids get put into the 75. We would allow randomization to evenly split up the kids, smart and, I don't want to say dumb, but lower level, into both groups. Same thing with Mr. Lipinski's. What time of day they take the test. Some kids take the test in the morning, some kids take the test in the evening or in the afternoon. So we would allow randomization to put some morning kids and some evening kids into Mr. McNair's 65-degree room and some morning kids and some afternoon kids into Mr. McNair's 75-degree room. That way they're getting a nice even split here. Now, is randomization going to guarantee that that happens? No, but it does allow us to have a very good chance that it will happen. Same thing with the level of or how much the students study. We will hopefully allow randomization to put some kids that study a lot into the 65-degree room and some kids that study a lot into the 75-degree room. Kids that study little will be in both rooms as well. So we can allow for three different things here to help us control for these extraneous variables. Direct control. Keep everything the same for everybody. So we're going to make sure everybody uses the same textbook, everybody uses the same instructional strategy. We can control that by direct control. Blocking allows us to control for an extra extraneous variable. How do we pick? Well, we have to try to pick the one that's most important, and we thought teacher was that. So therefore, we have each teacher having both treatments, 65 and 75 degrees. Randomization can cover for all those other kind of variables that are just impossible to necessarily control for. Some things like how much a kid studies, we can't choose that. So we can allow that to stay. Now, so now all of a sudden, rather than just, hey, you kids do it at 65, you kids take it at 75, go, see what happens. Now we've actually thought about and controlled for many extraneous variables, and all of a sudden we have a much, much better, well-planned out experiment that hopefully can tell us if the temperature in the room will cause higher or lower test scores. Another vocabulary word I want to teach you real quick is called a confounding variable. Now, a confounding variable would be, for example, if at the end of the day, I'm not sure if basically confounding variables occur when you don't plan, like we just talked about. For example, if I don't plan, I could say, the teacher is confounded with the test score, meaning the teacher is confounded with the temperature, meaning is it the temperature or is it the teacher that causes higher test scores? Same thing with study habits. Study habits could be confounded with the temperature. Was it the study habits that made them do better, or was it the temperature that made them do better? Again, these three items, direct control, blocking, and randomization, could help control for those types of confounding variables and make them not confounding. So we talked about two important items there, so I want to make sure you have a chance to write them down in your notes. An extraneous factor is one that's not of interest in the study, but is thought to have an effect on the response variable, like the teacher. We weren't interested in the teacher causing higher test scores, but we thought it was an extraneous variable, so we had to try to get rid of it. Two factors are confounded if their effects on the response variable cannot be distinguished from one another. So was it the teacher or was it the temperature? We call those confounding variables. So hopefully that example helps make sense. So what about other factors we cannot directly control for? So for example, somebody might say, well, gender. Boys do better than math than girls. Okay, or maybe girls do better than math than boys. So maybe gender is something that we can't control for. Home life. Maybe some kids have a better home life where their parents really push them and support them to study more, and other kids' parents don't do that. So those are two quick examples of things we can't control for. So what do? Well, once again, we allow randomization to evenly put boys and girls into both temperatures and evenly put people that have good and poor home lives into both temperature groups. Therefore, if we have, think of it like this, if we have both boys and girls in both groups, then how could you tell me that boys caused the lower test scores? Because in the low test score group, there were girls as well. So that's why we allow randomization to really help us control for all those little things that we can't control for. But if you haven't noticed, the whole point of a good, well planned out experiment is to really, really take the time to think about these extraneous variables. Excuse me. All right, let's think about another example here. And I want to take you through the steps and try to explain everything that's going to happen here. So let's say we have a waitress, and the waitress is interested in thinking, if I write thank you on the bills that I give to my, people at the tables, the people eating, if I write thank you on the bill, will that cause them to potentially give me a higher tip? Now, the tip amount is obviously dependent on the size of the bill. So let's say the percentage of the tip amount. So the explanatory variable in this waitress's study, the explanatory variable will be whether the check says thank you. So we'll say the thank you of the check. That's the explanatory variable. And the response, I don't want to just say the tip amount because obviously the tip is connected to the size of the bill. So we'll say the percentage of the bill that they leave for the tip. So being very clear on how you're going to measure your response is important. So now we talk about the factors. Remember, the factors is the explanatory variable. So another word for explanatory variable is factor. So my treatments are what I'm going to give out. So the treatments that I'm going to give out, some bills are going to say thank you. Maybe with a little smiley face afterwards, right? Or the second treatment is nothing on the bill. I will write nothing at all on the bill. Okay? So what are some extraneous variables that could potentially cause somebody to give me a bigger tip or not? Well, how I treat them as the waitress. I'm thinking like the waitress, how I treat them. So the one thing the waitress has to do is she has to control and treat everybody the same, regardless of if she writes thank you on their check or not. Another thing she has to control is the timing that their food comes out. So once again, maybe she really can't control that because she's the waitress, she's not the cook. So she has to hope that both groups get some people that get their food on time and some people that maybe don't get their food on time will go into both groups. So she's going to have to allow randomization to take care of that. Some people might say that men tip better than women. I don't know. So she has to hopefully hope that there are men in the thank you group and there are men and women in the, say nothing on the bill group. If she really, really, really thought that one of these variables was extremely important, she would need to block. For example, maybe some of her tables are by a window, and people that sit by a window get a nice view outside, and that would cause them to maybe give a better tip. So if that was really an issue, then we should block, and we should make sure that all the people that sit by the table, some of them get the thank you on their check, some of them don't. People that sit away from the window, some of them get the thank you on their check, some of them don't. So the purpose with blocking is you separate into purposeful groups, and then in each group they get each treatment. Okay, so that could maybe be something we do as well. These are all things you want to think about. Now, how do we determine who gets the thank you and who doesn't? Well, it needs to be done randomly. So how do you do this randomly? Well, this is kind of a tricky one. Some people might say, well, approach each customer and before you give them the bill, flip a coin and heads or tails. If it's heads, you write thank you. If it's tails, you write nothing on the bill. Well, the problem is that what if every time you flip the coin, it comes up heads? Then all of a sudden every single person gets thank you on their check and you never really can explore the topic more. So the idea is that's kind of a poor idea. You should be done randomly, okay? So maybe it's something as simple as every other. So the first person would be flipping a coin. The first person you'd flip a coin to determine, do I write thank you or do I not? And then every other table after that you switch. So if the first one says thank you, then the next one says nothing. Then thank you, then nothing, then thank you, then nothing. Okay? Something as simple as that could work. Okay? And those are all kind of I'm just trying to go through things you need to think about when you run a very good experiment. That way, at the very end, she can determine, did me writing thank you actually create bigger percentage of the bill for my tip? Okay, so these are all things that the waitress need to think of here that would cause really a good experiment. Another thing you can think of is blocking. Maybe she works on 2 days a week. She works on Thursdays and Fridays are kind of bigger nights to go out. So Fridays could potentially cause more um, more of a bigger tip or for some reason. So then she'd obviously have to block on Thursday and Friday, making sure that on Thursday she does both thank yous and nothing on the bill, and same with Friday. Because if she does all thank yous on Thursday and no thank yous on Friday, then obviously your results could be biased because you didn't split it up. And then somebody could say, well, the reason why they gave you bigger tips was because it was a Friday. It had nothing to do with what was on the bill. It was a Friday night. People give bigger tips on Fridays. These are all things that you need to consider when you do run an experiment. Okay. All right. Let's talk about one more example here. And the example is, which fertilizer is best for growing grass and with how much water? Okay. Well, let's see here. Let's say that I have 3 different fertilizers. So I have fertilizer A, B, and C. And I have watering once a day or twice a day. Okay, 2 times a day or 1 time a day. So now, what are my explanatory variables? So there are 2 things that are going to explain the grass growing. The explanatory variables, or the factors, would be the fertilizers and water. So fertilizer and water are the 2 main things that are going to cause the grass to grow. Now the response. How am I going to determine this? Okay, well, I could measure the height of the grass. Maybe I could somehow measure the thickness of the grass based on per square inch, how many blades there are per square inch. Maybe I could actually have a professional come in and I could have a professional actually judge the grass, somebody that really knows about grass growth or something. But my point is, you got to really understand, how are you going to measure that response? Now, my treatments. Everybody tends to get treatments and factors confused. So the factors would be the 2 things that factor into the grass growing, fertilizer, water. The treatments are the different groups. See, if I have A 1 time a day, B 1 time a day, and C 1 time a day, well then what about getting twice a day? So the idea is the treatments would be A 1 time a day, A 2 times a day, because I really need to discover maybe A 1 time a day is better than A 2 times a day. Okay, I need B 1 time a day, I need B 2 times a day, I need C 1 time a day, I need C 2 times a day. So those would be my 6 treatments. So it's important to understand that you have to be able to list all of your treatments out that you're going to give out to the grass. Okay, so now what are some other things that potentially could cause grass to grow besides fertilizer and water? Well, sun is a potential confounding variable, right, or an extraneous variable. Temperature. What else can we think of here? Maybe wind, right? Soil type, grass type. There's many different types of grasses, and I'm sure this is a short list of many things that can determine how much grass grows. So the idea is, I need to make sure that all of my plots of land that I use get the same amount of sun. So that is using direct control. They all are in the same temperature. So they're all right near each other, all in the same temperature. If they're all right near each other, they should all be getting the same amount of wind. I need to use all the same soil. If I use all the same soil type, I'm controlling for that. I'm using all the same grass. I'm going to use Kentucky bluegrass. It's the only type of grass seed I'm going to use. See, if I use different grass seeds, somebody might say, well, that grew better because it was that kind of a grass seed. Oh, that grew better because it was nice, very nice, moist soil. That's why it grew better. Oh, that grass grew better. Oh, that was because it was in the sun. So if I keep all of those things the same, then all of a sudden I can't claim it's any of those things. It really is the fertilizer or not. So maybe I have 60 plots of grass. And maybe somebody says the size of the plots matters, so I want to keep them obviously all the same. So those are all examples of direct control. So of my 60 plots of grass, let's see, I have, how many groups do I have? I have 6 treatment groups. So that's obviously 10 at each level, right? So I'm going to have 10 plots are going to get A, watering 1 time a day. 10 plots are going to get A, watering 2 times a day. 10 plots are going to get B 1 time a day. 10 plots will get B 2 times a day. 10 plots will get C 1 time a day. And 10 plots will get C 2 times a day. Okay? And then what I can do at the very end is I could compare all of these together to determine which one really grew the best, highest, thickest grass. Okay? And as long as all of these other extraneous variables are kept the same, then all of a sudden I can't claim that any of those things were confounding with the grass growing. So these are all kind of things you have to think of when you do grow. Now, I want to quickly talk about what happens if somebody says, you know what, we can't control for the sun. It just so happens that, let me kind of show you this with the picture. Here's my plots of grass, right? And this side gets a whole lot of sun and this side gets no sun. Well, now this is something I cannot control for. I can't control for this, so maybe we allow this to be blocking. So we cut the plots of grass down the middle. 30 are in the sun, 30 are not in the sun, and we block. So here's my 60 plots of grass, or plots of land, whatever, and these 30 are in the sun, and these 30 are not in the sun, not sun. So now what I do is, of the 30 in the sun, I have to make sure 5 get A 1 time a day, 5 get A 2 times a day, watering, 5 get B once, 5 get B twice, 5 get C once, 5 get C twice. And then I have to do the same thing here. 1, 2, 3, 4, 5, 6. I'm kind of being sloppy here, sorry. Obviously, you would be much neater on a test or something. But these would be the 5A1, 5A2, 5B1, 5B2, 5C1, 5C2. So now blocking, again, allows us to control for something I couldn't control for, like half the plots getting sun, half not. But if I allow it to be up to randomness, maybe this entire side, maybe it'd be rare, but maybe this entire side all gets treatment A. And this entire side all gets treatment B. Okay, well then all of a sudden it was because it was in the sun. That's why it grew. It had nothing to do with A or B. So if I make sure that each side gets A1, A2, B1, B2 on each side, then all of a sudden I have essentially controlled for something that was uncontrollable. Okay? All right, so now what I want to kind of go over is a couple of, I want to leave you with some spot to take some notes here. These are 10 questions that you want to be able to answer when planning an experiment. So the first is, what is the research question that data from the experiment will answer? Make sure you truly understand what the research question is asking for. Make sure you also understand what the response variable is and exactly how are you going to measure that response variable. So how will the values of the response variable be determined? Also, what are the factors? What are the explanatory variables for the experiment? Okay. Then you're going to go on to number 5 is, for each factor, how many different values are there? So fertilizer, there were 3. And then for water, there were 2. Well, 3 times 2 is 6. So that leads us to part number 6. What are the treatments for the experiments? The treatments would be A 1 time a day, A 2 times a day, B1, B2, C1, C2 as well. So making sure you really think about the explanatory factors and what are the different treatments that they will create. 7 is really make sure you think about those extraneous variables and how they might influence the response. And then how does your design incorporate random assignment of the subjects to the treatments? Like I said, how do I determine which 5 plots of land get A1 and which 5 get A2? Got to be done randomly. Got to be done randomly. Yes, I blocked because they were in the sun, but after I block, who gets what has to be chosen randomly. So every plot of land gets a number, 1 through 30, and then the first 5 get A1, the second 5 that come up get A2, and so forth. So you got to really explain that, once again, using random number tables. For each extraneous variable in question 7, how does the design protect against it? Its potential influence on the response. So did I use blocking to control for that variable? Did I use simply direct control? Or did I allow randomization? Because remember, randomization could allow you to control for the uncontrollable. Will you be able to answer the research question using the data collected in this experiment? So when it's all said and done, will you really be able to use your data to answer the research question truthfully? As long as your study and the experiment was all done very, very correctly, and thinking about all these 10 things, you can hopefully then determine, does X cause Y?